Okay, so let's take a look at a few example problems that deal with bisectors and triangles, perpendicular bisectors, and angle bisectors, and the ideas of those things being concurrent or intersecting at the same place. So in the first example, it says the perpendicular bisectors of triangle ABC are segment PT. Let me just kind of highlight these as I label them out. Segment PT, segment QT, and segment RT. So those three objects there are our perpendicular bisectors. So remember, that means that their point of concurrency, which would be T, that's called the circumcenter of our triangle, and it is going to be equidistant from the three vertices, right? T, which is our circumcenter, is equidistant from A, B, and C. So what that tells us is that T to A is the same as T to B is the same as T to C. Now we see here that T to C is equal to 6, right? So part A, which asks about the distance from A to T, well, that's the same as from T to A, right? Those two things are the same. So we know that's going to be 6. Now part B asks about, what about R to C? R to C. Well, that's this distance right here. We want to know this distance. How are we going to be able to find that? Well, it all goes back to the idea of what a perpendicular bisector does. Remember, a perpendicular bisector does those two things. It's perpendicular and it bisects. So if segment RT is a perpendicular bisector of segment AC, we can see that it's perpendicular to it, making a right angle, but it will also bisect segment AC. So from A to R is the same as R to C. Well, if AR is 5, RC is the same as AR, so it's also going to be 5. So that's how we can find segment RC. Now, as a bonus question here, what if we wanted to find the length of RT? What if we wanted to find this length? Let's call it x, right? We could still do that because we could use the Pythagorean theorem and we could find, we can look at this as the right triangle where we know two of the sides. And we could say, well, that x squared plus the 5 squared would have to equal the 6 squared, right? That's that a squared plus b squared equals c squared idea. And you could go ahead and solve that and find out what that distance is. And theoretically, that means you could probably also do it for segment QT. Well, we already know segment PT, but maybe we could say, let's find segment PB's length. We could do that. There's a lot of things we could do if we just started applying the Pythagorean theorem to some things that are happening in this picture. But that's example 1. Now let's go ahead and scroll down and take a look at example 2. Okay, it says two of the angle bisectors of triangle ABC are AP, so AP is an angle bisector, and BP. BP is an angle bisector. So we know, first of all, that that means that these two angles would be congruent. If AP is bisecting an angle of the triangle, it must be bisecting angle BAC. And we know that this angle and this angle are congruent. And that also means that P right here, right, is the incenter of triangle ABC. P is the incenter of triangle ABC. So that would mean that it is equidistant from all sides of triangle ABC. So what segments in our picture are representing the distance that P is from the sides of triangle ABC? Well, that would be segment PK, because we can say that it's going over and making a right angle. Segment PJ and segment PL. Those things should all be equal. P to K, try and write that K a little bit better. P to K is equal to P to L is equal to P to J, right? But P to J is listed at 5. So for part A, PK, that's going to be 5, right? these would all be 5 units long. Part B says find the perimeter of triangle APL. Well, triangle APL is a right triangle, right? And, well, actually, we know all 3 sides. It's got a side of 5, a side of 12, and a side of 13. So the perimeter would just be 5 plus 12 plus 13, which would be 30. Now, well, I guess, okay, let me take that back. We didn't know that segment AL is 12, but we knew that this side is 5 and this side is 13. And we could have done, I guess, let me back that up. Where did we get this 12? We did 5 squared plus AL squared equals 13 squared. So that's going to be 25 plus AL squared equaling 269. If I subtract the 25 from both sides, then not 269, it would be 169. AL squared is equal to 144. So AL is the square root of 144, which is 12. That's how I found that to be 12. And then I could add the 5, the 12, and the 13 together. Okay, so let's move on to example 3 then. In the diagram below, it says if the measure of angle BAF is 15, so let's go ahead and put 15 degrees there. But we see that's marked congruent to that, so we could also put 15 degrees there. CBF is 52 degrees, CBF, so that means that one is 52 degrees, but that would also mean that angle, ABF, is 52 degrees. What is the measure of angle ACF? Okay, interesting. Angle ACF. Well, what do we know about this? In this picture, I see that ray FB is bisecting one angle of triangle ABC, and ray FA right here is bisecting another angle of my triangle. So that means F must be the incenter again, right? F is the incenter of triangle ABC, which would tell me that ray FC, or we'll say segment FC, is bisecting angle ACB, right? Because FC must be the third angle bisector in our triangle. So this angle is congruent to this one. But if I look at if I go back to looking at triangle ABC, I know that the measure of angle BAC is 30 degrees, 15 plus 15. I know the measure of angle ABC is 104 degrees, right? 52 plus 52. So if I add those together, that's 134 degrees. The measure of angle ACB, this third angle of triangle ABC, would be 180 minus 134, which is going to be 46 degrees. So angle ACB is 46 degrees. Okay, then the measure of angle ACF would be half of that 46 degrees, which is 23 degrees. This would have to be 23 degrees. And I know that again because I decided that ray FC, or segment FC, is bisecting angle ACB. I found out here that angle ACB is 46 degrees, so I cut that 46 in half, and that's angle ACF right there. All right, so that's what I did for A. Now for part B, let's look at part B. It says if EF is 3y minus 5, okay, let's go ahead and put 3y minus 5 for that segment. And ray DF is 2y plus 4. What is the distance from F over here to segment AB? Well, again, F is the incenter of the triangle. So since F is the incenter of the triangle, that tells me that F is equidistant from all sides of triangle ABC, Or in other words, that from F to E, since F to E, we're working our way over to the side of the triangle, but we're going perpendicular to it, right? F to E, which is the distance from F to this side, segment AC, would be the same as F to D, because we see the same thing happening. F to D is a segment that's perpendicular to one side of the triangle. And that would be the same as the distance from F over here to AB. Now let's sketch in real quick. Let's sketch in the segment that would be equivalent to FE and FD, right? The segment that's going to be representing the distance from F over to AB. And we'll call this point right here, maybe point G, right? So F to E would be the same as F to D, would be the same as F to G, that distance that we just drew in on the picture. Well, if I look at these two right here, that means I can take 3y minus 5 and say it equals 2y plus 4. And I can solve this by subtracting 2y from both sides, adding 5 to both sides. So I have y equals 9. And that means that FE, so FE would be equal to 3 times 9 minus 5, which is 27, minus 5, which is 22. FD, just real quick, if I was doing FD, that would be 2 times 9 plus 4, which is also 22, which is what we wanted to see, right? We wanted those two to be equal to each other. But then that is also then going to be the distance from F to G. They're all 22. And F to G we decided was what we were representing the distance from F to segment AB as. So there's our answer for part B.